Want to lose the time for your webinar. So good morning, good afternoon, good evening. Thanks for joining. This is our international webinar series on geoenvironmental engineering, sustainability, and resiliency. I am Krishna Reddy from University of Illinois, Chicago. This is a weekly webinar series. Many of you are attending regularly, so you know about this. But this webinar series is supported by ISMGE, Environmental Geotechnics Committee, ISMGE Geoengineering Education Committee, and ASCE Geo Institute Geoenvironmental Engineering Committee. So this is the upcoming schedule. You can see today we have interesting presentation. Next week we have another interesting presentation on incineration ash. The speaker has done a lot of work on it in Denmark, so don't miss that one. And we have this schedule for April, and then we have a couple of webinars in May. So if you are interested in receiving the certificate of participation, make sure you fill up a Google form. Link to that one will be posted towards the end of the webinar in the chat box, and you must fill it up before the end of the webinar, okay? So past webinars have been recorded and they are available on this YouTube channel. You can view, at your leisure time. And if you are new to geoenvironmental engineering or sustainable engineering, these would be the good resources to read first and then get into these fields. As you all know, we organize EGRWSC conference. It is an annual conference. The next one is coming up in June, and there is overwhelming response. Papers are being reviewed, and look forward to seeing many of you in June. So in terms of webinar logistics, as of yesterday, we had 448 registrations for this. So please mute your mic and switch off your video. And at the end of the presentation, you can show your video. First, we will have we'll take a group screenshot so that we will have faces associated with the webinar attendees. Type your questions in the chat box or raise your hand and you will be unmuted and you can ask questions directly to the speaker. So our presenter will answer as many questions as possible. If your question is not answered, I will provide you the webinar speaker's email address. You can contact him later. Again, don't forget to fill up that Google form if you are interested in getting that certificate of attendance. So today's presentation topic is very interesting, overview of slurry trenching and recent lessons learned. And no one knows this topic better than Dan Ruffing. He's the Vice President, Geo-Solutions in New Kensington in Pennsylvania here in the USA. Just a brief intro to Dan. Dan, as I said, he is the Vice President of Geo-Solutions. He completed his bachelor's and master's degrees in civil engineering at Bucknell University. And Dan's master's research was actually on soil bentonite slurry trenches. And his experience and expertise includes slurry trench cutoff wall construction, soil mixing, and jet grouting, and many other related topics. Dan has been with the Geo-Solutions since 2009. As the vice president, he is responsible for all technically oriented aspects of the company, including construction quality control. Dan has established himself as a recognized technical resource related to Geo-Solutions specialty construction techniques. He has published dozens of publications and made many presentations at conferences and technical short courses. Just the last couple of days, we were at the Geotechnical Frontiers in, at ASCE and ASCE annual conference, and he gave a short course on this topic. So without further ado, I want to thank Dan for agreeing to present this webinar in spite of his hectic business schedule. And thank you all for attending, and let's listen to the webinar and learn something new. So with that, I want to stop sharing my presentation, and I ask Dan to share his presentation and start presenting. Thank you so much, everyone.
Good, thanks for that nice introduction, Krishna, and thanks everybody for attending. Going to talk about slurry trenching today. Going to touch on some applications, some things that you might want to consider, and then really just go over some photos to show various aspects of the construction, just to kind of jog your thought process as you're thinking about this and thinking about ways to apply this technique. I'm going to start off with a brief introduction of exactly what slurry trenching is, because I wasn't sure what this audience was aware of. So essentially, slurry trenching is a natural extension of the concept of mud-supported borehole to create a deep and narrow trench without the need for a dewatering system or another sort of conventional excavation support system like trench boxes. So this little schematic kind of shows it nicely. On the left, you have a sand with a series of weights sitting next to the sand, that representing a building or some sort of other structure. As you start to excavate in the sand, obviously we all know that it's going to collapse. So in the top photo, you get open trench collapse if you don't support the excavation. In the bottom photo, you can see the little slurry trench in the middle. You can actually see the bentonite slurry penetrating into the sand soils, which we'll talk about here in a minute. And then you can see all the way on the right side of it, a deep, narrow excavation, slurry supported with a stable building right next to it. So the concept and the theory behind slurry trenching is that the bentonite clay particles in the water filtered out at the soil interface. This creates what's referred to as the filter cake, and that filter cake becomes the interface over which the fluid pressure in the slurry and the horizontal earth pressure of the particulate soil media in the formation soils, those pressures balance. That creates stability, and that's what allows us to excavate the slurry trench. So this photo shows the development of the filter cake on the side of the trench. Again, the filter cake is really just a thin cake of bentonite particles that have been filtered out at the soil interface. The actual cake and the stability of the trench are a little bit more complicated than just the fluid pressure and the lateral pressure applying to this one surface, but this is in its simplest form the reason that slurry trenches are stable. The more complicated story is that you have a particulate media, you get penetration of the bentonite slurry into the media, specifically in a cohesionless soil or gravel. That adds to stability. You get electrochemical attraction of the bentonite particles to the soil interface. That helps to build the cake and thicken it. All of this contributes to trench stability, and all of it is referred to as largely the filter cake. The slurry that we use for slurry trenching is an engineered fluid. It typically consists of bentonite suspended in water, though we can use other types of clay. And we'll also talk today about natural and synthetic polymers that can be used to create high flow barriers. In a well-mixed slurry, it's really impossible to tell where the clay or the polymer ends and the water begins. As you can see on the left, it's certainly visually homogeneous. So what are some common uses of slurry trenching? First, the most common use is that we can install a cutoff or a barrier wall. These walls are vertical walls installed to control horizontal flow. The media that we put into these walls is low permeability, which is used to slow or control the migration of water, typically water containing some sort of contaminant or impact. These are not impermeable. I say that because I often hear the term impermeable barrier, and really nothing is impermeable. Steel and concrete are close in some cases, but these walls do allow the flow of water. It's just much, much slower than you would get if you did not have the wall. And really, in a geoenvironmental case, we're trying to control contaminant movement by slowing advective flow. You still get flow through other methods, but the advective flow is the primary controller for contaminant migration, and installing a low permeability barrier like this dramatically slows that flow. We can also use slurry trenching to install collection trenches and drains. These are also vertical walls used to control horizontal flow, but the backfill material is high permeability. So we're actually encouraging water to flow into and through the barrier materials. This can also be used to control contaminant movement via advective flow, but by encouraging the flow to occur in the area that we want it to occur. Similarly, you can use polymer slurry trenching to install reactive barriers. These are also vertical walls used to control horizontal flow with the high permeability backfill material. And the water is encouraged to flow into and through the barrier. And the backfill media that is installed in these walls is designed to treat the impacted water as it flows through it. These are often referred to as permeable reactive barriers, or in some cases you can use sorbents, and those would be adsorbent barriers or absorbent barriers. Slurry trenches can also be used to install shear walls. These are vertical walls installed in the ground to stabilize the ground. Typically, we're not so concerned about permeability when we're installing a shear wall. We're more concerned about strength, namely measured through unconfined compressive strength. And relative to a concrete material, these might be 5 to 15% the strength of concrete, so 50 to a couple hundred PSI. Water is actually encouraged to flow around these barriers, and the systems are often designed to make sure that water doesn't build up on the backside, as that would increase the load. And in a lot of cases, these walls are installed perpendicular to the expected ground movement or beneath a structure requiring protection to intersect a slip plane. So what types of slurry trenching are there? This flow diagram kind of works you from the overall construction method of slurry trenching. We refer to it as slurry trenching because of it's a means to an end, right? We use the slurry to construct the wall. So there's a variety of different end cases that can be referred to as a slurry trench. There are 1- and 2-step installations, which we'll talk about here in a little bit. There are low and high flow barriers. There are different types of excavation slurries. So we talked about the bentonite water slurry. There's also polymer water slurries. And then there are self-hardening slurries, which consist of cementitious materials and some type of clay, typically also bentonite. And then whether or not you have a self-hardening slurry or a slurry just used for the installation, there may also be a backfill material. So those can range from soil mixed with bentonite clay, soil mixed with cements and bentonites, various types of aggregate materials that can be used in polymer trenching, and then various types of inert materials like gravel and sand for collection trenches and drains. And then the end product on the right side, the majority of these are cutoff walls or barrier walls. Some are collection trenches and deep drains, and some are reactive or absorbent barriers. So the most common type of slurry trenching is a 2-step process involving the excavation under bentonite water slurry and backfilling with a mixture of soil and bentonite. Typically, the soil that we use for this is the soil that's excavated from the trench, and the backfill mixing is performed alongside the trench. Once the material is mixed into a high slump consistency similar to concrete, it's then pushed back into the trench, displaces the slurry, and then this plug of excavation moves along until the wall is totally complete. On the right side here, you can see a soil bentonite excavation in progress. The excavator on the left is actually the excavator that's excavating the trench, and the excavator on the right is mixing backfill alongside the trench. Some more photos of soil bentonite slurry trenching. So on the left side, we're working adjacent to a canal to stop the flow of water from a canal into an adjacent swamp. And on the right side, we're working on top of a levee next to a small dam. So another way to install slurry trenching is to use a self-hardening slurry that becomes the final backfill. So instead of having a process where we use the slurry just to hold the trench sidewalls open, this product is used to hold the sidewalls open, and then it is also allowed to harden in place and form the final backfill material. So as you can see on the right, that's an individual standing on top of a slurry trench the day after it was installed. So the material is already hardened to a place where he can stand on it comfortably. You can see in the middle here, we have this big green cylinder. Show that to highlight that when you incorporate slag into the mixture, it gets this very emerald green color to it. And then on the left side, you can see that the installation looks very similar. You have an excavator excavating the trench and backfilling it with slurry. The bigger difference is there's not a whole lot of other equipment working nearby because we're not worried about creating the backfill. So this just shows a cement bentonite wall being constructed at the toe of a dam. With polymer slurries, we can install barriers that are high flow, not low flow. These are also two-step processes wherein we use a polymer slurry to excavate the trench, and then we backfill the trench with a high permeability matrix consisting of inert granular materials mixed with some sort of reactive agent. Most of these walls are sand and gravel and zero valent iron for the treatment of chlorinated solvents, but we've also done some strange combination of reagents that were used to treat a specific contaminant matrix. And really, the method allows any sort of material to be placed in the trench, the slurry trenching method being a means to an end. So if you can come up with a reagent combination that won't segregate in the placement through the slurry, then you can use permeable reactive barriers to treat any sort of contaminant material. This just shows the placement of a very high slump sand iron combination through a tremie pipe to ensure that the material isn't segregating during placement. So instead of a low permeability barrier or a reactive barrier, we can also use slurry trenching just to install a collection trench. So we need a deep drain. We want to collect the groundwater. We want to prevent groundwater migration offsite by directing it into a treatment system. You can use the slurry trenching technique to, again, install a deep, narrow trench without dewatering or excavation support, but backfill that trench with an inert granular material. And it may or may not include horizontal or vertical collection piping and a variety of other structures used to encourage the movement of the groundwater into the treatment system. So on the left side, you can see a polymer trench with vertical wells being installed, and then that would be backfilled with the granular material. On the right side, we can see a trench being installed with both vertical wells, a sand backfill, and also a filter fabric on the outside of the trench. So how are these slurry trenches constructed? First thing, we have to excavate the trench. Most excavations are performed with an excavator, typically a long stick, long boom excavator like that shown on the left side. If we get below 27 meters, we have to kick to a different excavation technique, that being with clamshells, which are shown on the right side. This is just a different view of a slurry trench being excavated from the operator's seat. And I show this to show that, this is what the operator's seeing. These operators are very skilled at feeling the ground through the excavator. As we call it, they're digging in the blind all the time. So it takes a very specific skill set to excavate these trenches in a productive manner. At the end of the excavator, you have a variety of different types of excavator buckets. On the right side, you can see what's called a V-bottom excavator bucket with rock rippers on the back. The V-bottom is designed to maximize the amount of down pressure that the machine can put on bottom so that we can rip up a rock interface or a densely packed till or any sort of key material that we're trying to put the trench into. There's a V-bottom in the middle as well that does not have the rock rippers on the back. And then the one on the left side is a flat bottom bucket with the rock rippers at an offset so that at any given moment, you're only engaging one or maybe two of the teeth, which allows you to apply a larger pressure. Once we excavate the trench, if we're doing a two-step process, we have to perform the backfill mixing. As I noted before, a lot of times when we're excavating these trenches, we're placing the soil adjacent to the trench, we're mixing it with bentonite, and then we're putting it right back in the trench. That's what's shown on the right side here. In other cases, we don't have the room adjacent to the trench, or maybe we're incorporating a cementitious component or a large dry bentonite component that requires significantly more quality control. In that case, we might have a remote mixing area. So in this photo, you can see the road coming in from the top. The trucks are bringing the soil from the trench. They're putting it in a large pit, pre-mixing it with bentonite to get it to an initial slump. And then the excavator that's shown in the center of the photo is taking scoops of that material, it into a mixing cell, adding cement and additional dry bentonite, ensuring that it's a nice homogeneous mixture, and then loading it back into a truck, and it goes to the right side of the photo, down back to the trench to be placed in the trench. Another photo of backfill mixing, where instead of using an excavator to mix the backfill, the site is using a dozer. You can use all kinds of different equipment adjacent to the trench to mix the backfill and place it at the head. This shows the placement on that same site. So we have the same dozer right here mixing the backfill, tracking back and forth, and then this excavator is taking the mixed backfill and placing it at the head of the slope to create the final barrier wall. If we're doing a self-hardening wall, then we're creating a mixture of bentonite and cement that requires a batch plant. This is what we refer to as an automated batch plant. It's constantly batching at a known set of reagent combinations to produce a slurry that has consistent properties on the back end. This is what we refer to as a continuous mix process. So this is not a batch process. We're adding all the reagents in the water continuously and monitoring the quality control via viscosity and density on the backside to ensure that we get the reagents in there. A little bit less accurate, but you can produce significantly more material in a shorter period of time. So this is an effective way of doing it on large projects. If we're doing a collection trench after or actually immediately prior to placing the backfill, we would be putting the collection piping in. If there's a horizontal component, you have to weigh it down with weights installed at some horizontal distance along the pipe. And then you would backfill over it with the granular material. So just some example applications. In the top left photo, we have a site in Michigan where we were installing a combination of soil bentonite and self-hardening barrier walls around a contaminated site. The bottom photo is in West Virginia. We're installing soil bentonite barriers, a lot more room on that site, so there was no need to consider the self-hardening walls. And on the top right, very small site, oil spill next to a creek. We installed a soil bentonite barrier because there was lots of room to do so. Other example applications, these are dewatering projects. The one at the top is in Florida, adjacent to potash mining facility. On the bottom, we're in Newfoundland. The wall is actually installed inside of that embankment to the right of the photo, and you can see the Atlantic Ocean on the outside of it. At this site, they actually did not put the wall circumferential around the excavation, like we'll see in some of the other photos I'm going to show. They ran a dewatering system on the backside to control water on the backside of the excavation and use the cutoff wall to control water on the front adjacent to the ocean. The left photo shows a project in California. The reason I show this photo is it shows how you can work in very tight areas. So you have 3 excavators working in tandem, moving the spoil material up and down the trench to get the backfill mixed. In the middle, we have a soil bentonite wall in Louisiana at the downstream of an dam toe. And on the right side, we have a soil bentonite wall being constructed through a levee adjacent to a canal and adjacent to a swamp. Top left, we have a self-hardening wall in Manitoba at a mining facility. So we used a self-hardening wall here because we were working on the crest of a dam, and the material that we were excavating was unsuitable for use. So a lot of times when the material is unsuitable for use, we switch to a self-hardening wall, which is an engineered backfill. We don't have to worry about what the soil is. We can just discard it and replace it with the cement bentonite. In the middle, we have a site in Kentucky, large hydroelectric power plant with a circumferential cutoff wall. I have some photos of the total site later. On the right side, we are installing a self-hardening cutoff wall through a dam crest. Again, the self-hardening wall here was selected because it has a lower footprint, and we didn't have to worry about trying to manage the soil along this narrow embankment. Oops. Bottom left, we have a site in Colorado, soil bentonite wall, lots of room to work here. So that's why the soil bentonite wall was selected. And this was for excavation through gravel layers to dewater a gravel pit for removal of the gravel and then the creation of a water control reservoir. The bottom right, we did a soil bentonite wall with an HDPE membrane installed through the groundwater table. And then that HDPE membrane was tied to an HDPE membrane at the surface. And then the entire site was vacuum consolidated for the expansion of a harbor. The same site in Smithland, Kentucky on the left side here, you can see that this was a deep wall. So we had a large long stick excavator digging down to about 27 meters. And then we had clamshells working behind it, digging down to about 55 meters. Another deep wall in the middle here up in Newfoundland, we saw the photo earlier. This shows a photo along the trench. So you have the clamshells working on the left side. The excavator would be working where the photo is being taken from. Then on this particular site, we encountered a lot of boulders. So we had drills that were working in tandem with the clamshells to drill through boulders when they were encountered. And in the background on the right side, you can actually see another crane that has a chisel attached to it to break up those boulders. On the right side here, we have a site in Bloomsburg, Pennsylvania, where we're installing a self-hardening cutoff wall through it's actually a flood control embankment, but it was adjacent to a factory, so there was very limited working room. On the right side here, we can see the Smithland site again. So you can kind of see where the wall was going around the future location of a hydroelectric power plant. So the wall was installed to help control water during the excavation of the hydroelectric plant. Then the hydroelectric plant was installed through the center of this site. And then the dam that you can see on the bottom portion here was shut down. On the left side, we're installing a slurry trench cutoff wall in addition to a grout curtain through an embankment on a site in Utah. Couple more applications here. So out in California, they have lots of sand levees. So it's very common to install cutoff walls through those sand levees to ensure that those levees behave as intended in flood situations. Utah, self-hardening cutoff wall through the embankment of a dam. And on the bottom here, we have a soil bentonite wall being installed adjacent to Devil's Lake in North Dakota to prevent flooding of the nearby homes. These photos show the use of self-hardening cutoff walls for the installation of shear walls at the Tennessee Valley facility outside of Kingston, Tennessee. This being related to the large ash spill that occurred at that facility in 2008. The solution to prevent movement of the ash after a future liquefaction event was to put a series of shear walls in beneath the newly constructed embankments. And these example applications show the collection trenches and the PRBs. On the left, we're installing an HDPE membrane into the wall to prevent contaminant movement via a different method, that being the HDPE membrane, stopping it. In the middle, we have a collection trench with vertical pipe risers coming out for collection of contaminants adjacent to a military facility. And on the right side, we have a permeable reactive barrier that consisted of sand and zero valent iron. Some things to think about as you're going through the design of slurry trench cutoff walls. Number one, when you're doing a wall alignment, you want to avoid radiuses and obtuse angles. It'd be better to replace those with right angles or chords at a sharper angle if possible. Always perform a bench scale study. If it's a contaminated site, make sure to assess the compatibility of the backfill material with the contaminants, particularly in the long term. As you're performing bench scale studies, you should always consider what full scale construction process is going to be and make sure that you mimic that to the extent possible in the lab so that your lab results are as applicable to the field as possible. And at the bench scale study, we have a lot of time. It's cheap. It's really good to look to understand the variability of the target properties. You know, if you have a large site, You might have significant variability in the soil horizontally and or vertically. And you should understand, if I add 1% bentonite to this part of the site, what kind of permeability is it going to produce? Is it going to produce the same on the other side of the site with a different soil matrix? At the design stage, we should certainly assess the water source. Where is the water source? What is it? Is it suitable? And suitability relates to TDS, pH, hardness, alkalinity, the presence of organic materials, oils, acids. All those things should be assessed to ensure that it's a suitable water source. When we're performing borings, we should at least put a boring every 250 feet. I would say significantly more frequent than that if possible. It's good to have some measure of in situ strength from a construction standpoint. So incorporating SPTs or CPTs is beneficial. And when you're performing the geotechnical investigations and doing these borings, it's a good opportunity to collect samples of the soil for future bench scale testing if it's a kind of wall that incorporates the on-site soils. From a quality control standpoint, the purpose here is to document what, why, who, where, how the work is performed. And really what we want to do is create a story that we can use to recreate the project at some future point if there's an issue and we're trying to understand what occurred. Quality control is not all about the post-construction testing. Obviously, the UCS testing and the perm testing that are performed off-site on field collected samples are very important, but it's also important to implement checks throughout the system, pay attention to how the process is occurring, what the properties of the component materials are, and maybe, hopefully, we can identify issues at one of these earlier steps instead of identifying them in the post-construction testing when it's too late to make a change. The big thing I'll say is that small details on the job site can become very important later. I don't have specific examples, but really just document everything when you're performing quality control or quality assurance on job sites. Some common issues that we see from a design standpoint: make sure that when you're drawing or writing up a specification, avoid performance and method specs. You have to pick one or the other. You can't tell somebody how to do it and also what they're supposed to accomplish with it. Ensure the specs are either open enough to include a variety of different construction methods or specific enough and completely applicable to a single method. What we see a lot of times is an open-ended spec that has requirements in it that are very specific to a single method. And that inadvertently creates a situation where the construction teams have to push towards one method, even though a variety of methods would work if that one section of the specification were removed. Early specialty contractor engagement is very helpful. Specialty contractors see dozens of these walls a year, perform dozens of these walls a year, and they perform those under the guidance of a variety of different engineering companies and for a variety of different owners. So drawing on that experience can be very beneficial, especially early in the project. As I said before, you really can never do too many borings. I have plenty of examples where they thought the site was investigated well and the geology was understood. And then as you're excavating a trench that touches every piece of soil, you're going to discover a lot of things that you didn't anticipate. If you're getting to the area where the depth change is going to cause a change in equipment, which is around 25 to 27 meters, you really need to understand whether or not it's going to go to that deeper depth, because as soon as you kick into the clamshells, the cost and schedule go up dramatically. So it's not just 1/25 increase to the schedule. It could be a 40% increase to schedule for that additional meter beyond 25. As you get to the bottom of walls and you're designing walls, one very important component of it is the bottom portion, which is referred to as the key, if it's being tied into a lower permeability layer. Really important to understand why you need a key, whether you need a key, and the extent of the key. So obviously from a design standpoint, it's more conservative to go to the deeper layer and to go further into the deeper layer, but that may not be necessary. And in a lot of cases, that excavation into that more challenging key material could drive your schedule and your cost up significantly. So from a book that I co-authored with Jeff Evans of Bucknell and Parsons, um, we put a little table in there. You know, it's hard to give budgetary ranges that are applicable to long time frames, but absent any other knowledge of the job site, the most cost-effective method of installing a cutoff wall is probably going to be a soil bentonite barrier. There are some in situ mixing techniques, specifically with some of the chain trenchers, that can be equal to or less expensive than that. And then there's a variety of other types of cutoff wall or other types of slurry trenching and alternate ways of installing a cutoff wall that are going to be multiples more expensive than that base concept with the soil bentonite wall. All kinds of things affect the construction costs, the method, the geographic location, access limitations, the depth of the barrier, the soil conditions, the groundwater conditions. Is there not local expertise? Are you bringing in national providers? Material costs range across different areas. Labor costs differ. Specifically, is it a non-union shop? Is it prevailing wage? Is it union? Again, we talked about the bottom details of the wall that can have a major driver on cost. Are there above ground or subsurface utilities? And then really the size of the project. Small walls are going to be more expensive. Large walls, you get the benefit of optimization over a larger area. As I noted, Jeff Evans and I wrote a book on slurry trenching. It's available on Amazon. Really good overview of the history of the technique, fundamental components, and construction methods. And we also co-authored a book on ground improvement engineering that covers a variety of different topics, slurry trenching just being one. And that was co-authored with Dave Elton, formerly of Auburn University. Krishna, I have some other stuff I can go through, unless we want to take questions, and then I can walk through that stuff if we have time.
And that's great. I think, I think you cannot find all the details that you have provided in terms of the construction of these slurry trench cutoff walls. Then, very, very valuable pictures to see, and you have more experience than anybody else I could think of on talking about construction of these issues. So maybe, yeah,